This is section 4.8, homework number 3. In this case, there's a proposed proof to this statement. If n is any positive integer that is not a perfect square, then square root of n is irrational. So this is a fact, like square root of 3, which is not a perfect square, then it is irrational. Square root of 5, which is not a perfect square, then it is irrational. So that's what we want to prove. Now, let's take a look at the proof. It begins with suppose not, which means proof by contradiction. So we assume it's negation. So when this is if then statements, the negation is, so the negation of P implies Q. The if then statement is P and not Q. So therefore we have to state this P and the negation of this Q. So let's check that. Suppose there exists an integer n such that n is not a perfect square, which is exactly this guy, right? It's just a restatement of this first part, and which is good, and the negation of this guy n is rational, which is the negation of this guy, so which is good. Now, by definition of rational number, so what is a rational number? If you remember, rational number is the number that can be written as a fraction of two integers where the denominator cannot be 0. So therefore, let's take a look at that. There exist integers a and b such that square root of n, this guy is a rational which is supposed to be ratio of two integers a and b, not the square root of integer of a and square root of integer of b. So that would be something doesn't make sense right there. This is not right. We can say square root of n is equal to a over b, where b is not equal to 0 and a, b, they're both integers. So therefore this is something not right. Let's check that. I feel like this statement 2, this is not right, right there. This equation is not right, and because it violates the definition of rational number, it doesn't meet that definition. And also the assumption in stage 1 should be that I think it is fine. It's certainly completely fine. So therefore this statement should not be, I'm not going to choose that. That would not be my consideration. Okay, so that's incorrect. Now let's continue to read. Because that's incorrect, consequently, the next statement would not be right, but seems like we do not have anything for that. But of course, the 3, let's read the 3. Without loss of generality, we may assume that a and b have no common divisors, which is certainly a legitimate assumption, because if a and b have common divisors, we can always cancel them out until they do not have any common divisor. So we can assume a and b do not have any common divisors. Okay, so this is good. Now squaring both sides, of course, because it's the proof based on this incorrect equation, we will look at this equation. Okay, squaring both sides of the equation gives that. If this were true, certainly this would be true. And multiplying by b gives mb equals a, so which is okay. So I'm not going to critique anything about that. That certainly follows from step 2. Of course, let's at the same time talk about if we do the same thing, let's square both sides. We will have n equals a squared over b squared, right? And then multiplying b squared, we will get nb squared equals a squared. This is supposed to be correct. This is not correct, but it certainly follows from step 2. By unique factorization of integers theorem, a, b, n have representations as products of primes that are unique except for the order in which the prime factors are written down. So this is certainly true. That's what the unique factorization of integers theorem states. That means here they can be written uniquely as a product of primes, and here also uniquely written as a product of primes. They are the same, except possibly the order of the primes may be different. For instance, suppose this can be written as 5 times 3 and this is 3 times 5. They're the same, but just the order may be different, but they should be the same, considered the same. That's what the number 4 says. Nothing wrong I can see from that statement. Okay, number 5, since n is not a perfect square, there is a prime factor p in n that occurs an odd number of times. Well, this is saying because n is not a perfect square, so therefore, n can be written as, say, p1 power n1 times q1 power n p2 power n2 times p3 power n3 and so on and so forth, right? pk power nk. So these are the primes and these are the number power of each one. For instance, if I say 72 equals 8 times 9, which is 2 cubed times 3 squared. So in this case, that's the p, this is the n, so certainly n can be uniquely written as that. So this statement is saying n is not perfect square, so n is not perfect square. Then there's a prime factor, so out of these prime factors, there has to be at least one that occurs an odd number of times. That means the power should be odd. That means if that's not true, if all these powers are even, then n has to be a perfect square. Now it's not perfect square, then one of those power has to be odd. That's what it's saying. This is certainly true. I see no problem with that. Now let's take a look at the next one. So therefore, let's call it the p. There's a p, which is a factor of n. The power of p is odd. That's what is this saying. So because we say p is a factor of n, therefore it's certainly because nb equals a and p divides the left hand side, p has to divide the right hand side, right? So therefore p is a factor of a, which is good. So I do not see any problem in these statements. Of course, all these of 3, 4, 5, 6, all these statements, there are some problems because of the error from step 2, but the logic from 2 to 3 and 4, 4, 5, 5, 6, no logic mistake. That's what I'm trying to say. Now 7 says, thus A and B share the common divisor. Now we only know P divides N, right? P divides N, but we do not know whether P divides B or P divides A. That's not something that we know. So therefore this 7 says A and B share the same common divisor. This comes from nowhere. I do know P divides A from here. I do know P divides M from the statement 5, but P divides B, that's coming from nowhere. So therefore 7 comes from nowhere. This is a flaw in this case. So I would say 7 does not follow from here. It's just coming from nowhere. And of course, the conclusion will not be valid because of the previous statement is not valid, okay? Now, so that's how I would do this problem. Let's quickly talk about, because we already stated, like identify the mistake right there. And then from here, we derive a correct step here, which this is not correct. This is false. This is correct. Now, we can certainly, let me quickly just talk through that. So take a look at this. Next step in this 4 and 5, okay, 4 and 5, actually 4 and 5. This n, this is true. There's a p which happens only odd number of times in n's factorization. So there's a p to the odd number, okay, to the odd number that's contained in n. So p to the odd number times some other factors of n, other factors of n, and that make up the n, okay? That's the n. N can be factored as a p raised to odd power times other products of primes, other factors. Now here's the thing. If you look at the B, so I'm going to say B, if B can be written as a product of primes, say the factors are, say, R1 B1, R2 B2, and RK BK, okay? RK BK. So suppose this is B. When you square it, and then all the powers of this, so if you square it, R1 2B1, R2 2B2, and so on and so forth, RK 2BK. So the thing is, all the powers are even. All the powers are even from the factors of the B. Now similarly, from the factors of A, so for A, suppose A is equal to, say, S1 A1 to the power A1, S2 to the power A2, and so on and so forth, L to the power AL. Suppose this is the factorization of A. Now when you square it, right? When you square it, do you see that all the powers of the prime, all the powers of the factors of A have to be even? That will be 2A1, S2, 2A2, and so on and so forth, SL, 2AK. Now, here's the contradiction, where the contradiction comes in. On the left-hand side, you see there's the odd power, a prime to the odd power, or put it in another way, a prime that occurs odd number of times on the left-hand side. Okay, all these are occurring on at least even number of times. Now on the right-hand side, which is A squared, all the powers are even, so they do not match. There's no way the left-hand side can be equal to right-hand side. So this is the contradiction. What's the contradiction again? Left-hand side, there's a prime that has odd power, but right-hand side, there's no prime that has the odd power. They are all even power. So that's where actually the contradiction comes in, and so that the supposition is not true, and therefore we prove the original statements. But as far as these problems concerned, these are the two statements that I should check. Those are the mistakes from this proof.